Appreciate that. Yeah, welcome everybody, and I'm excited to do this. I've been in this industry for quite a while now. Machining really is a big, not just my work area, but it's a big passion for me, and I really enjoy it and enjoy working on it, enjoy talking about it. So we'll try to do this in a way to make sure that we've got enough time for questions. And I've got some slides here, some things that we'll talk about, and we'll do this, kind of as informally as we can here. All right, so hopefully you can see my screen now. So where I want to start here a little bit is to kind of talk about different types of milling techniques. This is applicable whether it is solid tools, for instance, solid carbide end mills, or indexable tools. You can definitely apply this to either one. There's, a lot of different types of techniques that are discussed these days, and certainly a lot of this stuff that I'm going to talk about, I've probably been talking about for 15 to 20 years. But what's really changed is as we add more and more people using more advanced CAM packages, and especially add-ins to CAM packages, more of these techniques are available to people with a little less calculation and a little bit work, especially in complicated paths, right? So really want to kind of talk through the reasons of why you would use one or another, because it's kind of a topic that's kind of come up because I see that sometimes people don't understand the difference between the type of milling techniques, and also we'll go into some other, let's say, trade names or scientific names for these, but to kind of help you have a better idea of what you can use when and how to get the most out of a process. So kind of to start with too, before I really get into exactly what do I mean by dynamic or traditional, where I'd kind of like to just pause for a moment is talk about roughing versus finishing when it comes to milling, right? And the reason that that's important is, if I think about finishing off of a part, I'm almost always have a finishing operation to achieve the final tolerance, to achieve, for instance, wall straightness, remove cusps or scallop marks, finish with a proper radius, all those type of things, right? So almost always when I talk about finishing a part in milling, I'm going to refer to that as more of a traditional technique. It is going to be a low depth of cut, probably a lower cutting speed, because I am trying to finish that part, get it to the final specs. And I also might be worried, for instance, when we get in titanium machining for aerospace, I might, or Inconel, I might be worried about work hardened zones or white layer or things like that as well that I'm trying to do. So finishing, let's just say, is finishing. But when we get into roughing, that's when this topic really starts to come into play of how should I rough, right? And one of the things that I just kind of want to, again, mention before we get into this in terms of roughing is that a lot of people still have the idea that, if I've got a lot of stock to remove for a part, that I need some sort of roughing end mill. So, roughing end mill is in, typically it has some sort of chip breaker form, some sort of, let's say OD pattern to help separate the chips. And certainly that is a possibility. That is something that you can use. But let's say that is roughing with a roughing end mill. Where we get into this a little bit deeper is the idea that we can also use other end mill styles that would be capable of finishing as well and do some roughing operations, do some heavier stock removal. And that's where we really want to get into this topic, is that finishing is almost always going to be a traditional type of cut, and roughing, you get to pick. So let's start to dive into this a little bit. So um, let's talk about what I'm calling here dynamic milling. All right, and when I talk about dynamic milling, we could call this by a couple different terms. You know, basically, just as a simple definition, we're looking at a process of milling where we're using a tool path to keep a constant chip load even when the tool path isn't straight. And we're going to do this usually by varying the radial depth of cut. Okay. Sometimes that's called peel milling. Sometimes that's given a lot of different terms by different cam companies, for instance. But we're going to call it dynamic milling here, just to kind of have a constant term as we go through. When we talk about it, you know, in terms of when I talk to customers, when I talk to friends, fellow researchers about what am I going to suggest, when I get into dynamic toolpaths, I'm going to usually suggest that somebody tries to maximize their axial depth of cut, okay, if possible, while trying to reduce the radial depth of cut. And we're going to talk about this a little bit more. With that, that's usually going to give me the chance to add flutes, be it on a solid tool or be it on an indexable tool, and increase speeds and feeds due to chip thinning and how it changes heat generation. And we'll talk about that a little bit too. So if done properly with a good cam system, then we're going to utilize different arcing tool paths that you can kind of see over here to the right. That's going to help with entry and exit of the cutter engagement. So and one of the biggest things at the end of this is to get to more predictable tool life and try to achieve higher material removal rates. And so let's kind of just still stay here for just a minute and talk about what this means, especially compared to traditional cuts. Okay, so let me talk about traditional cut, and then I'm going to talk about a few other terms that you may hear, you know, used in the industry. So what do I mean by a traditional cut? I mean, traditional cut is, you know, if you think about it in terms like this, somebody had a part, your approach to the parts to figure out how to write the best possible, you know, G-code program to go at it, either in an older CAM package or, you know, by hand. I mean, a lot of us have certainly written a lot of, you know, paths by hand, right? But in a traditional cut, I'm usually trying to maximize my radial width of cut. And because of that, of course, as I increase my radial depth of cut, my forces go up. As my forces go up, I usually have to reduce my axial depth of cut so that I don't overload the machine or overload the part. And usually I end up having to slow down RPM, feed rate, because of heat issues. So, you know, probably a lot of you are familiar with, you know, the really old work done by Taylor in terms of tool life diagrams and things like that. You know, we're still interested in that stuff today, you know, but when we go into that, what are we usually doing? You know, usually we're testing different speed conditions, right? And we see that tool life kind of follows in a logarithmic pattern based on cutting speed. Well, the cutting speed on the same type of cut we're talking is directly influencing temperature. So if I've got another way to decrease temperature, then that can let me increase my speed. And if I can increase my speed, I can increase my feed rates and look to get more productive. And that's kind of where this starts to get into play. Now, the reason that I'm going to talk about both, and toward the end, you know, I obviously, as mentioned earlier, I work for Kennametal. I will talk about some Kennametal tools as part of this to use as examples. So I'm not in sales. I've never been in sales. This isn't a Kennametal commercial. But I will use some of our tools to kind of demonstrate different things that we have developed to try to target different types of cuts, and also how you might choose to use them. So let's get into a little bit more comparison of some higher level things, and then we'll go a little bit more in detail. One of the things that I'm going to kind of point out, and I'll recap this again at the end, is that number one, that there are advantages to both. If I want to just go in and take out a lot of material, a traditional milling strategy still could be the best way, but I really need to think about my part to start with. So let me give you a little bit of an example. If I were machining, let's say, a cube, and in that cube there's a pocket, right? I want to do the outside of the cube, I want to do the pocket. The depth of everything starts to become very important to me as I would analyze this, working with somebody. If the depth is such that, we're talking, I'm only going to use, half times the diameter of the cutter, maybe 1 times, maybe even 2 times, depending on the type of the tool. That starts to get me thinking about maybe a traditional approach could be better to take a big radial cut, because I don't have the advantage of going with a deep axial cut, right? On the flip side, if I can use a tool and really take advantage of the axial depth of cut, I'm almost always immediately thinking about a dynamic type of path, because I know that I can get my metal removal rate based on the axial depth. And now I can start to take advantage of the chip thinning and some of the heat issues that we'll get into. Doesn't mean that that's always the case. So somebody could certainly choose one or the other. For instance, you could still do a dynamic technique on the shallower pocket. You may choose to do that because you find out that it's Inconel 718, and tool life is going to be extremely poor. Maybe the fixturing of the machine is extremely weak, so you want to take advantage of forces, or you want to take advantage of tool pressure, things like that. So, but that's part of what we want to talk about today, right? Is the pros and cons of both, so that you know how to use both and you know how to play. The other thing that I would just kind of say to everybody is that it's always different based on your situation. So one person's finishing is another person's roughing. And what do I mean by that? Well, if I'm going and I'm talking to somebody that is working in very large forgings, and they are using large diameter cutters, and they're removing a huge amount of stock. Well, a finishing, cut to them might be a similar stock removal as somebody that has produced a part by additive and is looking to clean it up and hit the finish tolerance after the additive process, right? So I see a little bit more and more of that coming into play. Print it, and there's now features that I need to mill. So, but when I look at that, typically on especially like an additive part, you may be choosing to mill some of those features that have very small corners, and those very small corners may call for a very small end mill. And so now when I compare the size of the end mill that I can use based on that cut, guess what? It's now a roughing cut. And so that's one of the interesting things, is that you shouldn't just assume one or the other based on the stock removal. You should look at the stock removal versus the size of the cutter versus the length that you can use to help make some of those decisions. And we'll talk about more at the end. And of course, yeah, I'm sure maybe we'll have some questions when we get done for that. But I want to get that out there just to get you thinking as we go through the rest of the presentation. So obviously, probably most of you have already read through a lot of the stuff on this slide. But I'm going to go through it a little bit, and then we'll start to talk about some of the science, behind this. So traditional milling strategy on the left. So what we call AP, that's going to be axial depth of cut. So maximum 1 times diameter usually. We do have some new tools that I'll mention at the end that in most materials we can increase that up to 2 times diameter, but usually you're looking at 1 times diameter. Dynamic type strategies, we're normally looking at trying to go 2.5 to 3 times D. Sometimes we're going even up to 5 times the axial depth of the tool. And we're going to talk about changing that radial depth of cut to go along with it, just to kind of give you a general piece of advice. Normally with a dynamic path, I'm normally looking to be in the range of 10 to 15% of the cutter diameter for the radial depth of cut. That could be less if I want to be extremely conservative about tool life. That could be a little bit more depending on the material, if it's an aluminum, for instance, wrought aluminum, something like that. But as an average, I'm normally 12, 13% as a general average, okay? Before we kind of hit into the bullets here, just what is ACPs? Probably some of you are asking that question. So that's going to be axial contact points. What in the world is that? Okay. Basically, what I mean by this is one of the things that I like to look at is when I calculate based on the radial depth of cut, the axial depth of cut, and the cutter diameter, I like to know if I drew a straight line up the axis of this tool, when I find where it's fully engaged in the material, I want to know how many contact points, how many cutting edges are engaged axially. Because that's really nice when I want to look at how I want to stabilize the cutter. So when I get in traditional milling strategies, because of the short depth, even though I have a high radial depth of cut, I'm normally averaging about 1.5. So what does 1.5 means? It means sometimes 2 edges are engaged. Most of the time it's 1. So, you can expect, more of, let's say, the general deflection pattern. Here, it's a little bit more stable in a dynamic path because you're contacting more areas. The other thing that you can kind of think about here is think about if I looked at this as a cantilevered beam and I summed, did an integral of the force, right? I'm moving that force more toward the shank. I'm changing the bending moment a little bit more in comparison to what I have in traditional milling strategy. So you can kind of think about that. I'm putting the force here more in a bending mode. It is a force that has a little bit more, let's say, cyclic action to it. In other words, of on and off type. Versus here, I'm going to be a little bit smooth and I'm going to be a little bit farther up. So that's one of the things to kind of keep in mind. So in general, when I kind of compare the two, let's say the advantage of a dynamic path, feeds and speeds are normally going to go up. We're going to talk about why that is. Forces and pressure are normally going to go down, and we'll talk about why that is. Axial engagement, I'm going to drive up. Radial engagement, I'm going to drive down. We talked about that. Vibration, we just talked about that a little bit. Tool life, we'll get into these things together. Corner machining, we're going to talk about corner machining specifically as some things to look out for. But in general, process stability based on this temperature is one of the most important things to kind of realize between the two. And again, this is going to be different based on the material that you're working in. If you're working very heavily in aluminum, you can get process stability with either. In general, you can get process stability with either. But when you get into especially high temp alloys and titanium, we generally are going to find more process stability, more predictable tool life with a dynamic strategy. So let's kind of jump from that a little bit further. Before I talk about this, let me just talk about 3 terms that definitely you'll hear in the industry and of course see in papers, and these are great terms. So one is HPC, high performance cutting, One is HSC, high speed cutting, and one is HEM, high efficiency milling. Now, we're talking about all three of those today lumped into this. It's not at all that I don't like those terms. I think they're great, to be honest. I think that sometimes people struggle a little bit to tell the difference between the three of them. So I'm going to describe it just a little bit so you have an idea. But then you can kind of see how that lumps into what we're talking about today. So HPC, or high performance cutting, is typically based on taking heavy chip loads, heavy radial depth of cut, lower cutting speed, but maximizing the torque of the spindle. That to me is how I'm going to tell you to do a traditional cut. Because of course, or what I would call a traditional cut. For a lot of people are going to think of that slow. I personally don't do slow, okay? my job is to make things go fast. So when I talk about maximizing traditional cuts today, I'm not talking about running an old Bridgeport. I'm really talking about HPC type of stuff, heavy chip load, heavy radial depth of cut, max the spindle out that way, okay? High speed cutting is going to be a little bit the opposite. It's going to be a lot of what we're talking about on the dynamic side of small radial depth of cut and increasing the spindle speed because of the drop in temperature to get some speed back. The biggest difference between, in my view, between HSC, so high speed cutting, and HEM, high efficiency milling, high efficiency milling is more what I'm going to be talking about, where it's combining the high speed cutting and it's just maximizing the axial depth of cut. Okay, so hopefully that helps if you've seen those terms. Again, very good terms. I just, I find that a lot of people get mixed up with them. So if we can kind of talk about some of the fundamentals behind it, then it should make it easier to go through. So let's talk about chip thickness for a little bit, and then we can get into this a little bit more. So if I kind of look at this diagram here, right? So I've got an end mill, I've got a radial depth of cut, and certainly I'm moving it at a certain feet per tooth, feet per revolution. In general, for this, I'm going to look at feet per tooth in terms of my uncut chip thickness, right? And I can look at this as when we refer to HX, that's the maximum chip thickness. There's also an HM that you'll see in some literature, which is an average chip thickness. Europe tends to use more HM in calculations. I really like HX because I'm usually trying to look at what's the maximum possible damage to the tool. But as long as you use one and stick with one, you're fine. The biggest thing to note, regardless of that, is just simple plane geometry. I've got the same arc here and I've got the same arc here. Anytime that my radial depth of cut is 50%, so one radial distance, that uncut chip thickness is going to be the same as my feet per tooth. Okay, that's going to be my maximum. But if my arc of engagement based on a lower radial depth of cut, as that goes down, you can see simple geometry, right? The distance here horizontally is going to be exactly the same between those two curves, but the chip gets thinner and thinner and thinner. And that's what we refer to as chip thinning. That is the big power here that we're going to use. So when we get into, when you got into high-speed cutting and then kind of turn that into high-efficiency milling. So again, what I'm talking about together in terms of dynamic techniques, what I want to see is, we are designing these cutting tools, be this a solid or be this an indexable. We're designing that edge to be able to take a certain maximum chip thickness. So the first thing is to max that out, okay? That's kind of rule number one. And there's some good reasons of of why I would want to max that out, right? I mean, the main thing is productivity. If I am if I'm taking a very small depth of cut, then I'm going to have some significant problems depending on the material, right? So if the material is especially elastic, then I'm going to have a big chance that I'm got a significant portion of that chip below the minimum depth of cut. I've just got elastic deformation. Then I'm going to have some plastic deformation. And then finally, hopefully, I've got a section thick enough to actually shear and make a chip. But in those elastic and plastic sections, I'm generating a huge amount of heat. I'm doing a lot of work with very, very little benefit, right? And, you know, given the material type and material properties, I could also be work hardening the surface as well. So, you know, that's something to keep in mind of why I would like to maximize that chip thickness if I can, okay? And so this, you know, this used to be something that we would teach people how to calculate, try to get them to input the changes to their CAM system. Now, of course, you see a lot more that it's automatically calculated for you. The one thing that you have to keep in mind, and we're going to talk about this as we get a little further in, is how this changes in corners and other changes of direction. Where, you know, you think that you have a certain radial depth of cut, maybe you go around a corner and you're taking off the same, let's say, stock removal, right? But as you change the path of the cutter, as the vector path changes, I could engage more of it. So that's one of the things to kind of keep in mind that we'll talk about a little bit more. But the first thing is that once we drop below that traditional type of cut to more of a dynamic cut. So again, you know, I said earlier, I normally am keeping this in kind of the 10, 12, 13% range. I definitely need to take advantage of chip thinning and increase the feed rate. Now, let's talk about the heat effects a little bit. And I'm going to show this kind of from two viewpoints. So the first thing is obviously just, you can see the same thing in the other one. Once we drop down and we start to have a small radial depth of cut, we've got a small arc contact width. So that's going to do really two things for me, right? Now my out of cut area for cooling is a lot larger than my contact zone. So because of that, I can get more cooling to the tool. That's an important thing. The other thing is if I kind of think about it from like a heat flux point of view, so I'm generating heat in this area, you know, how large is that? So how large is that relative to the tool? But this is a very kind of powerful thing to start thinking about, is that I've dropped my radial depth of cut, I take into account the thickness of the chip, I compensate for that, but I'm going to get a lot more time for cooling with this type of dynamic cut. The other thing that comes into play, and this is a lot less, let's say, evident on the surface, but one of the things that I really like researching is specific cutting energy. So I have tons of dynamometers, pro-micron spike systems, strain gauge systems, all sorts of stuff. We make a lot of cutting force measurements. That's something I really, really like. With those cutting force measurements, of course, we can get into specific cutting energy. So how much energy does it take to remove a certain amount of material, right? So here I've got, in a comparison, two different chips. So I'm kind of looking at that uncut chip area again, okay, at two different radial depths of cut. But for that radial depth of cut, I kept the maximum chip thickness exactly the same, okay? So did a quick little simulation, pop this in CAD, put it here. What happens is this deeper radial depth of cut is going to generate, you know, just by geometry. Again, I'm controlling this section here, I'm controlling this section here, but geometrically, this gets so much longer and thinner. And so we just kind of talked a little bit about, we've got an elastic region of this chip formation, and we've got a plastic region of this chip formation. And finally, we get to where we actually shear. We get enough deformation, right, that we start to shear and make a chip. But we're significantly angering the material, right, in this zone, and we're creating a lot of friction. We're creating a lot of rubbing. We're causing dislocations, but with no real output. So if I compare these two, this shorter chip, just based off of its geometry, is so much more efficient, and this leads to a drop in specific cutting energy. Now we know, of course, and that a huge percentage of our energy is converted to heat in machining, right? So with that such a high percentage, a nice little drop in specific energy here also directly leads to we are generating less heat. So again, we've got the cooling time area, we've got the area for heat flux, and now we've got where we're actually producing a more efficient chip because we're causing less rubbing. Okay, so that's some things to kind of keep in mind. These are some speed factors that I use, and we publish some of this stuff. This is also available in our what we call our Novo system that you can download and get recommendations. But if I am making a full slot, I'm actually going to drop off of my recommendations, and as I start to decrease, I'm going to significantly increase that cutting speed. So I'm not going to break down all of this. I just want to kind of talk briefly that, when I look at traditional milling and I look at dynamic type milling, I've got different type of tools that I can recommend. And these are different type of tools that, my team has developed specifically to target both the material and the type of cut. And I'm just going to talk a little bit about them so that you have some idea kind of what we're looking for, and we'll get into that. First, I'll show you a little example here. So this is off of our Core 5DA end mill, which is designed specifically for this, for aluminum. So this is a 5-flute end mill. It's through coolant, and it has a specific chip splitter profile. I'll explain what that means in a minute. But if I compare that, so all of these 3/4 inch diameter tools, to making a traditional 2-flute or 3-flute cut in, this was 6061 aluminum, I find that I can significantly increase my material removal rate at a lower radial depth of cut, but in this case, in this part, I could maximize that axial depth. I could go ahead and drop it down. So I drop it down, and with that reduced radial depth of cut, I'm going to add flutes, like we talked about earlier. I'm going to get more points of contact to stabilize the tool. So even though, here I'm fully burying these tools, 100% radial engagement. This is making a slot. But, 2-flute, I can basically go 1 times deep. This 3-flute, I can go half of that. But here, this is how much I was able to increase the material removal rate with the same basic setup, significantly higher inches per minute because I'm putting more flutes into the cut, right? And I've also taken advantage of that chip thinning. One thing to keep in mind, of course, is the type of machine. So typically dynamic cuts, because of the reduced forces, are easier on most machines. Usually I can take a smaller machine, a smaller spindle connection, and get more out of it with a dynamic cut. One thing to keep in mind is if you get into something like aluminum with, extremely high cutting speeds, RPM available, you might be looking at a very, very fast table travel. And that's, then something to keep in mind. I'm just going to point out a few things to kind of keep in mind, and then we'll try to finish with a few tool types and then get into questions. One of the things that I just want to kind of raise as you start to look at some of this on your own, especially if you evaluate either CAM packages or you do some of these calculations on your own, when you get into certain paths, either corners or in this case, like a trochordal cut, if you were using a trochordal slot, um, your maximum radial depth of cut, or your AE, may not be what you think it is. Because again, this is an example of the cutter is moving in a circular pattern. So I'm saying that I'm taking off this much depth of material. That's my step over, right? But when I actually draw it out and look at it in terms of how much arc of engagement I have, it's actually much, much bigger, okay? That's just something to keep in mind. The other thing is the same thing in internal radii versus external radii. So you can kind of see here, if I'm doing a circular interpolation and I'm making a hole, basically, I have a much significant more for the same, let's say, stock removal. I'm engaging a lot bigger area of the cutter. So that's something to keep in mind, especially also in helical interpolation if you go in to maybe make a pocket. Versus external, I can fly external for the same stock removal because geometrically it appears as a shallower AE. Okay. Corners. So this is something to keep in mind, is that when you're looking at milling cutter selection too, if you're dealing with a pocket or an internal surface, obviously you're going to look at the corner. And a lot of times, you're going to think about what tool you can pick based on how big the pocket is, how big the feature is to get in, but now you've got to consider the corner, right? You've got to finish off that corner. The relationship between the size of the tool and the size of the corner radius is very important. Let's see if I can minimize this. So yeah, I don't know in Zoom if you have to minimize that or if you see it now better with me minimizing it. But this is a comparison of two different radius sizes in a corner with the same stock removal and the same diameter of cutter. And what you'll see is that as you go into the cut, so you're engaging a 28% arc, and we could calculate that to work with the chip thickness. But as you get into the corner and you start to make that path move around the corner, the smaller the corner radius is compared to the tool, the larger it's actually going to engage. And what does this mean? This means that I have to slow down in this corner, okay, to maintain my chip thickness. So it's just something to think about how those two match up. The other thing is when to slow down. I would prefer to slow down before I enter the corner, because if I don't slow down until I hit the corner, like here, I'm already fully engaged. So if you want to be super conservative, you could back off, let's say, half the diameter on the length. You can obviously trig it out to figure out where you should make that transition. And I just bring this up because sometimes people go and try a dynamic technique where they're used to using traditional techniques, and man, everything ran great, had tons of tool life, it sounded great, and all of a sudden it snapped. What happened? Well, when you've cranked up your conditions, right, and you have, let's say, an interruption, and that interruption here in terms of the path changed the dynamics of the situation, that's when you run into a problem. So that's one of the biggest things, is to kind of think ahead. And this is where, so often what I find, whether it's dynamic or traditional, but especially traditional, a lot of times people had a bad experience. They were running a job, they were running a part, something happened, something broke, scrapped apart, whatever. What do? They usually back off, and then they usually take how much they backed off and applied it to everything else. Usually that's not really good practice, right? Because there was some reason for that part, that situation, that caused the situation. And obviously a lot of times, people don't do that extra digging. I'm just kind of offering here that this is a very common situation that will cause that. And if you can smooth that out ahead of time, you're in good shape. Avoiding sharp corners. This is an application example from some aerospace customers of trochordal milling, coming through, and what happened at the end. So they're using trochoidal to make a slot in a dynamic fashion. Once they break through the end, now you have significant amount of deflection here. The cutter's rotating this way, can come back and snap. You can think about things like, hey, if I came through and roughed this out a little bit from the other side, or if I stopped before I broke through and came back to the other side, how can I minimize some potential danger areas? So let's talk just real quickly about roughing tools versus chip splitter tools. I'll show you a couple tools and we'll do some questions. So kind of on the left here is traditional roughing profiles. Again, be this on following an indexable tool or a solid tool. But you can see when you overlap those patterns, so different flutes will move it axially up and down, but you always end up with a surface that isn't perfectly smooth. So on a lot of our tools for dynamic, we offer what we call chip splitters. And what do I mean by chip splitters? They're small interruptions along the flute that are designed to axially shorten the chip. You know, if I take a high helix end mill at a really deep axial depth of cut, I'm going to have a very long chip to have to deal with to get out of a pocket, to get out of my chip hopper, things like that. So we'll design in as an option on certain tools, chip splitters that will not overlap. So if I put it all together, I still can machine a finished wall surface, no problem, but they will axially shorten the chip. So this is kind of a comparison. This is in titanium of our Core 6 tool versus a typical rougher profile. You know, these are great for power consumption, right? But they're all going to stick together. And they're very short, but they're also big problems to get out of the machine versus same type of machining path, dynamic machining path versus traditional path. You know, but here I've got chips that are actually quite easy to take out of the machine. I'll just play this just very quickly here, just so you have some idea. As I pick these chips up, you know, they tend to stick together, right? And that's a little bit of a chip removal nightmare versus if I go and pick up the same type of chips, or not same type of chips, but the same type of cut, but made with a tool that we've specifically designed for dynamic milling. Yeah, just much easier situation to handle, right? This is just an example of wall finish off of a tool, off of our Core 5 aluminum tool on some 6061. So you can just see, even with those chip splitters in place, doesn't affect the wall finish at all. So just kind of finally here, I'm going to mention a couple different type of tools and close. In terms of traditional, where we have tried to bring some new things into the market. Again, if you've got some short axial areas and you really want to go in, take that heavy radial cut. We have developed a tool in the past 2 years called the Harvey 1TE that we launched. There are some very specific areas of the flute that really help us to increase the axial depth and the radial type of cut that we can make, as well as lowering the forces. So we go down about 25% in specific cutting energy typically with this tool compared to a normal 4-flute carbide end mill. What's really nice with this tool, in steel, we can go up to 2 times D slot, full slot. We've done 1 and 1.5 times D very easily in titanium and even Inconel, cast iron, lots of other materials. So the idea of this is, even though I've talked a lot about dynamic techniques today, again, to have the idea that you could use both, because again, some applications you're going to be better off with a traditional path. So we wanted to attack that. This is the tool I just showed a little bit from the Core 5 DA, special flute form, lots of cutting edges involved. This chip splitter pattern that we talked about. This is another version of it for for ferrous materials. You can also use this in Inconel as well. Same thing with some chip splitters down it. We also have introduced a new tool called the Core 6 PT, which is really targeted at titanium. And that's kind of the end for the tools there. So I'm going to stop sharing here for a minute. And let me just kind of conclude a little bit. So the other thing to kind of keep in mind, we talked about thinking about traditional, we talked about thinking about dynamic. The other thing to keep in mind is what I call combo sets. So, I like to play golf. Don't know if any of the rest of you are golfers out there, but that's kind of a more popular, thing in golf technology is to say, hey, I don't have to have the same type of clubs, same type of irons, top to bottom. Let me optimize certain ones in a certain way. Let me optimize another ones in a certain way. You can definitely look at putting the two together. If I want to be really productive and I've got a lot of pockets to make, I might take something like that 4-flute TE tool I showed, go in and blow out the center of it with a traditional cut, and then come in with a dynamic tool and finish the rest of it. That made me a great entrance. That TE tool can slot at 40 or can ramp at 45 degrees. I can go in, make a hole, and then run out from it with a dynamic cut. And save a lot of time overall. I've reduced the amount of work that the traditional tool has to do, so I've increased its tool life. I get really good tool life anyway out of the tool with a dynamic path, provided I don't hit into some of the pitfalls that we talked about. So that's also something to keep in mind, is the idea that just one solution may not be the best. You could combo the two together to try to get the highest overall productivity. Because at the end of the day, right, that's what we're all chasing is to try to provide the most productivity, the best parts in the different areas that we're working with. So, and again, like I said, always remember that one person's finishing cuts, another person's roughing cut. It might be only 1 millimeter taken off the side, but if it's got a 0.5 millimeter corner in it, somebody's using a really tiny end, right? So, so with that, I'll conclude and be happy to answer any questions that people have. And certainly, I hope this was helpful for you.